In section 16.11, we'll look at kinetic versus thermodynamic products of an addition to a conjugated diene. So let's look at the same reaction and vary the reaction conditions. So if I carry this reaction out at minus 78 degrees C, which is fairly easy to do with dry ice and acetone, what I end up getting is I get an 80% 1,2 product and a 20% 1,4 product. Remember, this is the 1,2 addition product. This is the 1,4 product. However, if I do the exact same reaction at 40 degrees C, I get a reverse. 20% of the 1,2 and 80% of the 1,4 product. Why is that? So we need to try and analyze what's going on here. In this one, there's less energy available. In this one, there's more energy available. So if we want to understand this, we need to look at the reaction coordinate diagrams of the two reactions. So they're going to both start at the same place because they both have the same starting material, 1,3-beta-diene. The one happens at low temperature, but not at high temperature. That's the minus 78 degrees C1, which means that it must have a lower activation energy. The other one happens at high temperature, not at low temperature. So what's happening in here? So if I look at this first one, I have a low activation energy, but my product is not as stable. Okay, so if there's little energy around in the environment, like at minus 78 degrees, it has enough energy to get over this activation energy barrier to make this product, even though it's not as stable. And so this one is called the kinetic product. It's easier to form, but it's not as stable. This one has a high activation energy. I'm going to put it down to here. Has a high activation energy, but is more stable, has a more stable product. So when there's a lot of energy around, this one can form, and is preferred because it makes the more stable product. And so we call this one the thermodynamic product. The next question I would want to ask if I were you is why? Why is the 1,4 product more stable? The simplest answer here is just to look at the alkene, and we have a more substituted alkene versus the 1,2 product. Here we only have a monosubstituted alkene, where here I have a disubstituted alkene. So if you remember from formation of alkenes, the Zaitsev products, the more substituted alkene is more stable. So that's fairly simple. What about the kinetic product? To understand why the 1,2 product is formed faster, we need to go back and look at the mechanism. So in the mechanism, the first thing that happens is this electron pair comes out and grabs a proton. And let's look at it in a little bit more detail than I normally would draw. As the proton is grabbed, the bromide leaves, right? So now once this occurs, the bromine immediately is very close still to the hydrogen because this bond just broke between the bromine and the hydrogen. So spatially, this bromine is much closer than it is. So if I draw the resonance form here, so the bromine is still very close to where that proton was that added. So for it to move over here requires diffusion. It has to pass through whatever the solvent or whatever the medium is that it's in, and that takes some time for it to move. So the faster product to form is this one, where the bromide doesn't have to take time and doesn't have to move through the solution. And if you think about with how temperature affects that, at low temperatures, things are moving slowly. It would take a long time. It would be hard for this bromine to move over to the other side. At high temperatures, things are moving much faster, and this bromide ion is moving much faster and can move over towards the other side, as well as because when things are at higher temperature, they can reach equilibrium. You can get the more stable product. So why is this one formed faster? Because when the cation is formed, the bromide is actually going to be closer to the one that's going to cause the 1,2 product than it is to the one that's going to cause the 1,4 product. So it's going to more easily form this one, then it will form this one, the 1,4 product.